Okay, welcome y'all. And this is the week 5 webinar. And the plan today, as always, I'll take any questions that you might have. Please, feel free to ask throughout the webinar. And then we're going to talk about sampling distributions. That may not make any sense right now, but it will in about 5 or 10 minutes. And we'll talk about unbiased and biased estimators. So if you have a survey and you want to say, well, what's a good guess for what you got? Okay, we'll talk about that. Then we're going to get into the most important theorem of all of statistics. Okay, and that is in any stats class, even math level stats class. So the question was, what calculator do we use for the uniform distribution? Typically just there's not much to do other than multiplication and stuff. So that's just any calculator that multiplies and maybe takes square roots if you're going to find a standard deviation. Yeah, so there's really not much in terms of the calculator for the uniform distribution. That totally changed in chapter 6 with the normal distribution, where you absolutely needed the calculator, or you have no chance. Okay, and that was with the normal distribution. And today we're going to be using the normal distribution calculator also. Okay, that's a good question, because uniform distribution it turns out mathematically is not very complex at all. So that's why you don't need anything fancy. But normal changes everything. So we're going to be talking about, as I mentioned, the most important theorem of all of statistics. And if you remember last week, we talked about the normal distribution. And I promised you that the normal distribution was the most important distribution. And the reason why it's the most important distribution is the central limit theorem. And we'll see in a little bit why that's true. So we'll have a central limit theorem that focuses on means when you have quantitative data and you want to look at the mean. Then we'll look at the central limit theorem focused on proportions. So that's when you have the yes/no question. You've asked a bunch of people, and that's also turns out to be the central limit theorem is going to apply to it. And then finally, the central limit for sums. So sometimes you're more interested in the total amount that you have versus the average amount. And it turns out the central limit theorem works for that too. So a couple reminders. The first one, this is an odd week. So since it's week 5, so there is no exam to do this week, but there is something very important, much more important than the exams, which is, the project. So it's very important. It's very important that you get that project done. And I want to remind you that the very last chance for you to send it to me as a draft for me to look at before you submit the final version is Thursday at 8 a.m. But better would be today or tomorrow, because if you wait till Thursday at 7:59 a.m. and there's 8 other projects that come in and they take a few hours each, it might be a couple days before I can get back to you. Okay, so whereas if you send it today, probably get back to you today. Might get back to you tomorrow, but the point is that what I do is I do the first sent, first read rule. So the first one that gets sent is the first one I read, and so on. And then I submit lots of feedback. And what I found is that those who do not submit their draft almost always do much worse than those who do, in terms of statistically, by the way. It's not 100%, but it's statistically true. So it makes a big difference, because what I can do is I can give you all the things you need to improve on, so you can take that maybe C project and turn it into an A project, okay? Or a D and turn it into a B or something like that. Okay, no guarantees, because you still got to understand everything I tell you. And that's something that I only read the project once for the rough draft, but the tutors can look at it. Okay, especially Kyle, he's our embedded tutor. Okay, so that is that's the big thing that's happening. And then on Sunday, it's the absolute due date is Sunday night. I recommend submitting it by Saturday, and that way I say that for anything important. That's a life skill. And that way, if something goes wrong and something real important you have to turn in, then you have an extra day. Okay, so if you kind of like consider having to do it by Saturday, that gives you the extra day if you need it to Sunday. But you should try to have a goal on Saturday. And that's true of, again, anything that's real important. It's good to set your goal a little earlier than the last minute chance. So any questions at all about anything? Okay. So if there's no questions, I have a question for you. And you have to answer it. The rule is you don't have to answer it honestly, but at least give me an answer. If you don't want to tell me, give me an answer that's believable. And the question is the following. It doesn't sound like a stats question, but it's going to be. How many hours of paid work did you do in the last 7 days? I think I'm going to answer also because then we'll get enough. And I want all of you to answer. So how many hours of paid work did you do in the last 7 days? And don't say 3 million because you can't do 3 million hours in 7 days. So type in the chat box. Good. That's a lot better. Okay, so just gonna put them in order, which you don't have to do, but I'm gonna put them in order, and that is 0, 35, 40, and 50. Okay, so there's a few ways of looking at this. I'm gonna consider this everyone who's here, and that way we're looking at this as a population. Got it? Okay. So we're looking at this a population, and because it's a population, we can find the population mean and the population standard deviations. That's not usually the case in the real world. Usually you can't find the population mean and standard deviation, but this is just an example. So then I can go to my calculators. I can go to one variable statistics calculator. And I can type in 0, 35, 40, 50. I can click on population standard deviation. Yeah. So the question was in the chat was that for project 1 on the rough draft, do you email it to me? And the answer is yes, email it to me. That's the way you want to send it to me, is via email. Don't submit it on the project 1 submission because that's the final version. And then it gets graded as your final version and you don't get feedback, you just get a grade. So make sure you email it to me. And again, only one person needs to email it to me or should, so that and then I'll send it back and then share and then you should share your comments with your partners. The question was email via Canvas or personal email. It's all the same. You just don't realize that. when you send me an email via Canvas, it gets sent to my personal email. So whatever you want, I'm happy with. Sound good? Because to me, it's literally the same. Okay, as long as but make sure that you give me the draft itself. Okay, so I'm going to calculate, and the mean was 31.25. And the standard deviation was 18.8331. Any questions on calculating the mean and standard deviation? And again, we're calling this the population. I know it's a very small population, but it's the best we can do here. I'm gonna change this. Okay, so what I want you to do is I want you to at least somewhat randomly pick 2 of these values, 0, 35, 40, or 50. Okay, you don't have to, no, 2, not 1. And you don't have to tell me which ones you picked, but here's what I want from you. Pick 2 of the values and take the average of those 2 values. take the average of those two values, and that's something that I want you to put in the chat box. So, okay, so we have a 17.5. We have a 20. And anything else? All right, if we have just a couple, that's okay for this example. Okay, notice, and I want to really let you know notations that one of the tough ones in this particular chapter. And let's start with the stuff we already know, and that is use mu for the population mean, and we use x with a bar on top called x bar for the sample mean. Okay, and notice there's more than one sample mean. Okay, here's another one, 37.5. 37.5. I'm a little worried about that. If you pick two values, not sure how you can get 37.5. Because you just pick two of the numbers and add them up and divide by 2. I don't see 37.5 as one of the possibilities even. Oh, no, there it is. I see it. Got it. 37.5. I was looking at the wrong one. Okay, so those are some values. And by the way, there could be more. We're just doing an example. And then you could also write down what the standard deviations are. And you could tell me, but you don't have to because that's more work. Standard deviation of 2 numbers is kind of boring anyway. But I'm doing this just because we don't have that many that are here. So you can also talk about standard deviation. That would be S. So S would be the standard deviation with sample size 2. Do you see that? All right. So notice that, and hopefully you kind of would figure this, is that the X bars are not all the same. And one of the things you might say is, if you pick two values and found their average, let's look at the first one, 17.5, and that's the one you found. For pretend you didn't even notice the other, so that other people did. Then that would be your best guess for the population mean, even though it isn't the population mean. Is that clear? Any questions on that? Okay, and that is what sampling is all about, is you take a sample so that you can find a best guess for important things. And important things are things like the mean, the population mean. Because in the real world, you're not going to have population sizes of 4 that we deal with statistics. You're going to have population sizes of like sometimes millions or billions even. And you're not going to be able to ever find the population mean. And that's why you take a sample and use a sample as the sample mean as your best guess for the population mean. Is that clear? Any questions on that? Okay. Now, it turns out, well, we'll get there in a little bit, is that it really is a good guess, and we'll talk about what that all means. So we can look at all those sample means. So we had only 3, but you can imagine, like, let's say you surveyed 1,000 people in America, asking them, how about adults? 1,000 adults in America, asking them in the last 7 days, how many hours did you work? Okay. In that case, there are more possible sample means that you can end up with than numbers you even know how to say. It's actually more than a Google, if you know what a Google is. It's a huge, huge number of samples possible. There's no way you can get all of them. Is that clear? There's no way you could get every sample size 1,000 adults out of adult Americans. It's just not possible. But you can imagine it, because you can imagine, well, I can imagine anything, and maybe you can too. Okay, not imagine doing it, but imagine that there is such a thing as all the different sample means. And if you look at the distribution of all the different sample means, that is called the sampling distribution. Okay, that's called the sampling distribution. And it's really, really important. Okay, so 1,000 would be a sample. A 1,000 people or adults would be a sample of all Americans. And then tomorrow you do a different one and get another sample and get their sample mean. And then your friend could do another one and get their sample mean. And maybe everyone could do one. You get millions of sample means. Do you see how that works? And you can draw a histogram of all those sample means, and that gives you the shape of the sampling distribution. Any questions on that idea? Okay. When you have a distribution of numbers, in this case, sample means, then you could say, well, what are the statistics for those numbers? So what is the mean, the population mean of all possible sample means? You could ask that. So one thing you would do before you even ask it is give it some notation. And the notation we use is right here. So the population mean of all possible sample means from a sample of size n, so we're always going to be doing the same sample size, okay, for the example that you're looking at, then that we're going to write it as mu for population mean, and then sub x bar because it's the population mean of sample means. Anyone lost on that notation and what it tells you? Any questions on that? Okay. So in our example, by the way, you could take all possible samples of size 2. So a 0.35, a 0.40, a 0.50, etc. And look at the sample means or the average of each of those pairs. And then if you look at all those averages, that'll be the sampling distribution. The mean of all those averages will be the population mean of the sample means. Okay, so the wording today is one of the hard parts, the wording in the letters. And that's, notice we use mu and we use x bar because it's the population mean of sample means. Okay, so again, one major statistic you're always interested in it is the mean. What's the next most important statistic in this class after the mean? Hopefully you know. Yeah, the standard deviation. So if you have all the sample means, if we look at these little sample means, we had 17.5, 20, 35, 7.5. There'd be others too if we looked at them all. Notice they're not all the same, they vary. The standard deviation of these numbers, the 17.5, the 20, the 37.5, and all the rest that you could get, the standard deviation will tell you how much they vary. Is that clear? So the standard deviation of the sampling distribution is sigma, because that's standard deviation, and it's a population standard deviation, of all the sample means, so sigma sub x bar. Any questions so far? Okay. It turns out that because this is a lot of words, standard deviation of all possible sample means, most statisticians use the word standard error for that. So standard error means the standard population standard deviation of all possible sample means from a population with samples of size n. Any questions? It's pretty abstract, but that's why I had you do this example, because you can think of the standard deviation of all these guys, that would be our standard error. Any questions so far? Okay. So one of the things, if you think about it, if you looked at all different sample means, like we have some of them, but if we looked at them all, and took the mean of all of the possible sample means, any guess what you would get? For this example? Anyone who has a guess will probably guess it right. If you don't have a guess, you won't get it. Yeah, so mu sub x bar. Any guess what mu sub x bar would be for this example? Yeah, it's 31.25. So it turns out that the mean of all possible sample means is the population mean. And that's a big theorem. We won't prove it, but that'll be part of the central limit theorem, and it's very important. And what that tells you is that this is an unbiased estimate. So your 17.5 was an unbiased estimate for the population mean. Yeah, different means will have different outcomes based on what sample is used. Yeah. Yeah, the use of only one sample will have errors. If you used every single sample, took the average of all the averages, that's the mu sub x bar, then you always just get mu. Okay, any questions on that? Okay, so that is a big deal. And again, the sampling distribution, I'm going to say it again because it's so important. The sampling distribution for a statistic for samples of size n is the distribution of all possible sample statistics from samples of size n. So if you were able to get all possible sample means and you took the mean of all them, it'll never be wrong. Okay, if you only took one sample mean, yeah, you're not going to necessarily get right at the population mean because, maybe you surveyed a bunch of people, you just looked at the two people that worked the most. Do you see? So here's the thing. Do you have to take many sets of samples to find the population average? How many over 30? It turns out if you want to get the exact population average, good luck. You'd have to take every possible sample, and that's not even usually possible. Does that make sense? So more often, what we're going to do is we're going to say, we're just going to take one set of data. That's what we're going to be using. Okay, why do statistics companies edit outliers? So maybe you mean, why do companies that use statistics remove outliers? Is that what you mean? Okay, good. I just want to make, okay. So the idea is if you have a sample that's really small, like maybe a sample size, 20 or something, then the outlier could really change things. So often you remove the outlier, or often what you do, instead of taking the mean, you take the median. That's another way of getting rid of outliers. So we don't really use the theorem in practice. It's only theoretical. It's theoretical, but it allows you to say, this is my best guess. Okay, and you want to be able to say, this is my best guess, because I'm going to give you some examples where you may think it's the best guess, but it's not. Okay. Yeah, so let me give you this big definition that talks about this best guess idea. A statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. So what we had just said is that the mean of the sampling distribution is an unbiased estimator for the population mean. Does that make sense? Let me give you an example where you don't have an unbiased estimator. I'm going to give you an example that that'll make more sense than what we just did. Let's suppose you wanted to look at the height of all Americans. Got it? I'll even count children. Okay, you're going to look at the height of all Americans. And what you're interested in is the range. Okay, and hopefully you don't remember what the range is of numbers, right? Then let's say you did a survey. Let's say you did a survey of 20, how about 35 Americans? Make it over 30, which was what the project told you to do. So let's say you looked at 35 Americans. And you looked at the range of those 35 Americans. Is that a good guess for the range of all Americans? Yeah, it's probably a terrible guess. Because if you looked at 35 Americans at random, you're probably never going to get you probably won't get anyone over 7 feet tall. Do you see? And you probably also won't get a newborn baby who was born in the last, 6 months. Because if you look at the range of all Americans, that's going to be that super high person who's maybe 7'9" or something. And that baby who was just born premature. And it might be like a 7-foot range. Do you see that? But if you randomly selected 35 Americans, the range will almost never be 7 feet. And the average of all your ranges won't even be close to 7 feet. Does that make sense? Any questions on that idea? So the range is clearly a biased estimator. You would never do a sample of 35 people in America to come up to like figure out what the range is of all Americans. That would not work statistically. Any questions on that idea? So the range is a very biased estimator. Is that clear? I'm kind of ignoring the next most important statistic when it comes to biased or unbiased estimator. Which one am I ignoring? Which one I didn't mention? I mentioned the mean and the range. Which did I not mention? Yeah, the standard deviation. It turns out the standard deviation is slightly biased, but not very biased. And it's too complicated to even get into in this class. Does that make sense? So I wouldn't ask you about the standard deviation because it's like not that biased. Just a tiny bit. Okay. And it depends how big a sample size you have. There's all kinds of, I'm not even going to get into the answers to that. It's just too messy. Okay. So, but what I want you to know is that the mean is an unbiased estimator. Okay. Yeah, the standard deviation is not reduced by 10 factors or anything like that. It's just too complicated mathematically. I'm not even going there. But what's the next most important statistic? Here's the hint. That isn't from a quantitative data. It's not from quantitative data. Median is quantitative. Turns out median is unbiased, but from something that's not quantitative, what's the only statistic we really look at for the yes/no survey question? Hopefully you know that is important. But the yes/no survey question, what's the only statistic we've ever talked about? I don't see you all jumping in. Should be obvious. All right, I'll tell you. The proportion. The proportion of yeses. Isn't that the only thing we ever talk about with the yes/no questions? Is what percentage of people said yes. And it turns out that is also an unbiased estimator. Okay, because you can do samples, you can get a proportion, do another sample, get a proportion, do another sample, get a proportion, take the average of all the proportions. Proportion comes from a non-quantitative survey question. So that would be a survey question. So a survey question might be something like, Do you live in South Lake Tahoe? The answer to that would be yes or no. Does that make sense? And the proportion would be the percentage of the proportion of people who said yes, because that's what you care about with the yes no question. And that's definitely qualitative, not quantitative. Okay, but you can still talk about it as an unbiased estimator for the population proportion, because you can take the average of all possible proportions. Any questions on that? Yeah, so if you ever can't figure out something, ask, I'll tell you. If you don't know what a proportion is, because that's actually a really important thing in our class is proportions. We're going to spend a lot of time on it. So the sample proportion is an unbiased estimator for the population proportion. Okay, very, very important. Any questions at all so far about this whole idea? Okay, so now comes the theorem. This is the most important theorem of this entire course. And here's the thing. If you grab a sample, okay, we could even talk about, the example I gave you, number of hours that you've worked in the last 7 days for money, okay? And, let's do something a little bigger population. Let's call it all adult Americans. And let's say you did a sample of 40 Americans that are adults. Then what you care about is your sample any good? Does that make sense? And what can you say from your sample? So one of the things that we've already talked about in chapter 1 is, does it represent the population without bias? And that's all about, making sure you do a good sampling technique, stratified sampling, representative sample. Okay, but then the next thing is, all right, so you let's suppose you did an unbiased sample, and you'll see you asked 35 people. You find their average. Okay, we've already decided that average is a good best guess, right? How good a guess is it? So let's suppose that you asked 35 people, and let's say their average hours of work was 37 hours. Then would you trust 37? Okay, so there's a question, if a company does multiple strata, is that better? The answer is yes, but I want to let you know for the project, if you're doing stratified sampling, just do one, otherwise it's too complicated. And I don't want to like torture you with like really complicated stuff. So for our class, we're sticking with single, but in the real world, yeah, you multiple strata. And you try and see what's going to be the bias and try to avoid the bias using multiple strata. But not for the projects because it's just too much work. Sound good? I'm just trying to learn stratified sampling instead of like do the best possible thing, which would be many, many hours of work. Okay. So again, if you looked at the sample mean for the sample that you got in number of work hours, and I said, what did I say, 20 hours or something like that, then is that reliable? We know it's a best guess, but let's suppose you got 25 hours is what I said. Let's suppose you got 25 hours for the sample mean work hours of adults. Okay, well, here's the thing. Could it be 26? What do you think? If you got the sample mean with a sample size of 35, could it be 26? Do you think it's likely that it might be like 1 hour off from what you got? If you got the sample mean of 25? What do you think? Okay. It could be 26. Could it be 49? Is that likely or is that unlikely? Okay, it would depend on the standard deviation. Okay, probably not. It's an outlier. Okay, but the big question is, what is the standard deviation? Okay, and here's the big theorem. It goes into what we said about means. It's going to do the standard deviation. And here's another issue. Let's say you wanted to actually calculate the probability that it's, say, within say 2 hours of what you found. So if you got 25, then you want to find what's the probability that's between 23 and 27? How would you find that probability? Well, the first thing is, do we know the distribution? Do you have any idea what the distribution of work hours is? By the way, I don't. Maybe you do. Any idea what the distribution of work hours is? Any of you have an idea? And I don't, by the way. So if you don't, that's fine. If you do, that's kind of cool. Okay. You'd have to discuss how many hours there are in a week. But we know how many hours are in a week. That's 7 times 24. 168, right? That's not a problem. So the key is we do not know. We do not know what the distribution of work hours is. We do not know that. But here's what's so great. If you're looking at the distribution instead of work hours, if you're looking at the distribution of all possible sample mean work hours with sample size, say 35, we actually do know the distribution. Because if you don't know the distribution, you can't find the probability. It's not possible. But if you do know the distribution, you can find the probability. So here's the big theorem. And this is called the central limit theorem. And it says the following. And this is central limit theorem for means, which is probably the most important of all of them. And it says the sampling distribution for the sample means from samples of size n has mu sub x bar equals mu. That one I already talked about. That means that the sample mean is an unbiased estimator. And here's the next one. Sigma sub x bar equals sigma over the square root of n. Okay? This is really important. Notice, if n is, let's say, 1,000,000. Let's say you surveyed 1,000,000 American adults, okay? Which still isn't that many compared to the 300 and, maybe 250 million American adults. Let's say you surveyed 1,000,000 American adults. That'd be a hell of a lot of work. But let's say you could survey 1,000,000 adults. Then the standard deviation would be reduced by the square root of 1,000,000, which is 1,000, by the way. So your standard deviation would probably be tiny, which means that your estimate, your X bar that you got, is very, very, very likely to be close to the population mean. Any questions on that idea? If you surveyed instead, let's say you surveyed 9 people, then your standard deviation is only going to be reduced by the square root of 9, which is 3. And that's a much smaller reduction. Still a reduction, but it's not that big a reduction. So the bigger the sample size, the more reliable your sample mean will be. It's a proof that the mean is good with a large sample size. Okay? And here's what I'm not proving is the central limit theorem. Anyone know what you need to do to fully understand the proof of the central limit theorem? Any thoughts? 8 years of calculus? Yeah, so you need to be a math major. Yeah, you need to change your major and be a math major and maybe even do more than undergrad because the proof is pretty intense. So the one thing you can do is trust me because that's what I did. And it really does work. So central limit theorem is true. And it was done a long time ago. Okay, over 100 years ago. So it's an old theorem, but it's true. Okay, and plenty of people with PhDs in math have verified it. So there's no question about it. Okay, this is number one, A and B. Here's number two, which is amazing. If the population's distribution is normal, or if the sample size is large, in our class, our different definition of large will be greater than 30. Okay, so I did tell you with the project one that 30 was to get you ready for the future. Well, we're there. And in our class, if you're greater than 30, then the sampling distribution for the mean is approximately normal. Okay, which means that we can calculate probabilities if you have a sample. Okay, if the population distribution is normal, it's normal. The problem with that is it's very hard to start with a population distribution that's normal. That's kind of rare. But sample size greater than 30, that's not that hard to do in the real world. So again, one of you said that you had someone who is does that for a living, market research, and that person will need the fact that you need over 30 so that you can actually have reliable data or that can give you reliable numbers in probability. And if you're over 30, you have that because you can use the normal distribution. If otherwise, you have no idea what the distribution is, and you can't do much of anything. Any questions on that idea? Okay, so this is a biggie. This is the most important theorem of all of statistics. And I've never heard anyone say that's wrong, that they think something else is more important. Everyone agrees this is the most important theorem, and that is the central limit theorem. So have this one down. Okay, sigma sub x bar equals sigma over root n, mu sub x bar equals mu. Okay, so what I thought I'd do next is tell you something that has helped me in my career, lifetime, actually. I'll call it lifetime. It's a very good life skill. And that is how to make money in investments. Okay. So I don't know if you ever thought about it. Again, if you don't have it, sometimes if you're a student, you don't really have enough money to do anything with. Even when I was a student, I put a little bit of money in, a few $100s, and just so that I could make money, because I knew I could make more money using statistics for my money than not. So let me do an example that's really important to understand how the central limit theorem can actually be used to make money. Okay, and I don't mean making money to get a good job. I mean making money to invest your money. Okay, so here's a scenario. Let's suppose you have $10,000. Okay, I'm just using that number because it's an easy number. Let's suppose you have $10,000. You put it in the bank. Okay. Okay, what's the probability that you're going to end up losing money after 1 year? Okay. So here's the thing, and I'm just going to tell you because it should be obvious. Okay, and that probability that x is less than 0, okay, which is how much money you have. No, it doesn't depend on inflation or inflation, by the way. It doesn't depend on inflation. You could lose value in a year, but you can't lose money, okay? And yeah, you can't lose money. So that means the probability is 0, and that has to do, and again, we're assuming that you're putting it in, an American bank. I don't know if you know the law, but I have money in Bank of America, for example. Okay, that's the bank I use. And if Bank of America goes bankrupt, do I lose my money? Do you know? Okay, the answer is no. There's something called FDIC insured. Good. We do have some that know what it is. And the government will give me my money back. Okay. So that's just a note. The government would give me my money back. Okay. Now I actually looked it up. I looked at the mean interest for banks in the United States. looked at this yesterday, and it was 0.57%. Is that good, by the way? Better than zero, right? So I know for sure I'm going to make 0.57% on my $10,000. Do you think that's a good investment? Okay, probably not. Probably not. Okay, it's better than losing money for sure. But one thing you have to worry about is inflation is like almost pretty much always more than 0.57%. Okay. All right. So it's better than nothing, but it just, it's not great. It's 0.57%. So here's the thing. Again, we're assuming that you have $10,000. You have to decide what you want to do with. Okay. What's another thing that you can do besides put in the bank? And there's a lot of things that I'm gonna do some, but I bet you might come up with the one I'm thinking about. Yeah, let's say we put it in the stock market. Okay. So we're gonna invest in the stock market. So here's the thing. Okay, and I'm gonna do it statistically. Let's suppose you put your $10,000 into a randomly selected stock. Got it? Okay. And by the way, mu is 9% and sigma is 20%. Okay, there's a high standard deviation when it comes to individual stocks. The mean is a 9%. Is 9% better than what you get in the bank, by the way? Yeah, it's a whole lot better than what you get in the bank. Bank is 0.57%. Stock market gives you 9%. But here's some problems. Okay, we're going to assume, and by the way, worry about this word assume. What's the first, especially if you look at the first three letters of assume, beware. So we're going to assume that stocks are normally distributed because we're just going to invest in one stock. We're not talking central limit theorem yet. We'll get there. Okay. What's the probability you're going to end up losing money? So now we're going to say, what's the probability that X is less than 0? How do we decide? How do we find this probability? What are we going to have to do? It's not going to be that hard if you do it right. Yeah, we're going to go to the calculator. So I'm going to go to the calculator. Go back to the calculator menu. We have a normal distribution. So I go to normal probability. Okay. For X less than 0, what's the low? Right? To lose money, what's the low? Yeah, I can go negative and a bunch of 9s. Okay. Yeah, you can say negative 100, but since we assumed it's a normal distribution, you should do negative a bunch of 9s. Turns out you get the same answer no matter what you do within decimal places that you care about. What's the high? 0. Because anything less than 0, you lose money. So 0 is like the borderline for losing. The mean we said was 9%. Standard deviation we said was 20%. Any questions on that? We calculate. Okay. And we have about a 33% chance of losing money. Is that okay? The answer is maybe. Maybe. It depends. Let's suppose that this $10,000 let's suppose you need that in order to pay for your tuition when you transfer to a college next year, when you go to college. And if you lose your money, you're going to have to drop out of college. Then that would be terrible. Does that make sense? And having a 33%, a 32.6% chance of not being able to continue college, that's not okay. Hopefully you all agree with that, right? Okay, so you might worry. Yeah, you get 9%, which is a lot better than the 0.57% you get by putting it in the bank. But you have that problem in that you might end up losing money. And then if you lose money, you may not be able to afford the important things in life, like college or food or whatever it might be, rent. Any questions on that idea so far? All right, what's another plan? Any thoughts? Real estate, okay, but if you buy a single piece of property, that could go up and down also. Does that make sense? Yeah, let's talk about a mutual fund, okay? So instead, suppose you put your $10,000 into the Dow Jones Index Fund, okay? By the way, my guess is you've heard of it, but you may not know, there are 30 stocks in the Dow Jones Index Fund, okay? Now, what's the probability of losing money? We're going to assume that the Dow Jones is a representative sample and that the stocks are independent of each other, which is not perfectly true. So we're making an assumption here. Any questions so far? Okay, so now we have X bar is what we're looking at. We're looking at the average of the 30 stocks. Does that make sense? Okay, there's more technicality to it, which I'm not going to get into about average, but we're just going to assume it's an average. Got it? We're going to take the average of the 30 stocks. What is the mean of all possible averages of 30 stocks if the average of all stocks has a mean of 9% interest or increase? What's the mean of the average of 30 stocks? It's still the 9%. So that first one is a 9. Any questions on that? How do we get the standard deviation of all possible averages of 30 stocks? Any thoughts? Here's a hint. I'm going to insert. Let me. Oh, I think I'm in it already. Oh, I'm in it already. Yeah, we're going to use the theorem. The theorem says that that is sigma over the square root of n. And I think I have to view it. Let's see. There we go. Show equation toolbar. So I'm going to go fraction. My sigma is 20. And then we're going to be over the square root of n, and n is 30. Any questions on that? And then it helps 20 over root 30. I'm going to go to the scientific calculator. I can go 20 divided by the square root of 30. And it gives me this number, 3.651, etc. Notice that the standard deviation dropped a lot. Instead of the standard deviation being 20, it's now a little more than 3.5. It's not that big a standard deviation anymore. Any questions on that? Now, if we want the probability that X bar is less than 0, so losing money. So now it's X bar, not X, and that's what's important here. Our low will still be negative 999. Our high is still 0. Our mean was still 9 because the essential limit theorem says the mean doesn't change, but the standard deviation changes a lot. And that's this 3.65 number. And if I want the probability, now take a look at the probability. The standard deviation will not, no. It's a little complicated. It's a little complicated. The standard deviation is, we're looking at the standard deviation of the sample, which is not what we found. We never actually found the standard deviation of the sample. We did not find sigma sub X bar. We knew sigma sub X bar. Do you see? I didn't use a sample to get sigma sub X bar. I just did it in theory. So the unbiased estimator says, is the mean a good estimate? Is the standard deviation a good estimate for the population standard deviation? It's not the standard deviation of all possible sample sizes, samples of size n. It's a little different. Yeah. So take a look. Do you think that it's a good investment now? I have less than 1% chance of losing money. Much better. Okay, we did make that assumption that, this is perfectly diversified and all that. And the assumption is not quite right. I'll explain a little bit how you make it work so that the assumption is a little better. But the probability is 0.0068554 or 0.007. Let's go. Okay. It turns out the Dow Jones is not perfectly diversified. You need to do more. One way of doing it is it works better if it's, say, a retirement fund in the Dow Jones, because then it's over, especially if you're not that old. If let's say you're 30 years old and you want to retire at 65, then that's 35 years of it happening, and then it's actually very diversified. Absolutely. That's why Warren Buffett made the bet. He did better than that, and I'm going to talk about that in a second too. Something I did also. But he does it as a career. I teach. If I didn't just teach, I'd make a lot more money because I know statistics well. Okay. So to diversify what, in a single year, the Dow Jones is not as good. You would probably want to do a multinational index fund. And you'd also do something called REITs, which is real estate, which someone talked about. And you do combinations of those. And I do that, by the way. And I actually do much better than the Dow. I'm good with investing, and I always have been. So that's the good news. Okay. Good news for me, at least. But the point is, what do you think the banks do? Because you drop your $10,000 into the bank. What do you think the bank does with your money? Yeah, they beat the system. They go into the Dow Jones and real estate and other things, and they spend it, but they also invest it into places that are going to make a lot of money, and basically they're making money off of you. Does that make sense? They also loan it out to other people with a higher interest rate. So that's another diversified investment. So there's lots of diversifications that you can do. Any questions at all? Any questions at all on this? Okay, let's suppose that you want your standard error to be equal to 2. Okay, we got our standard error to be equal to 3.65. Let's suppose you wanted it lower. Let's suppose you wanted a standard error of 2 instead of, so you want it lower. So then how big a sample size would you need? So we saw the Dow Jones 30 is not big enough. It's not enough stocks because we end up with a standard error of 3.65. If you want the standard error to be 2, I'll show you as a little math to do. Then we write down the standard error, and the standard error is sigma over root n. That's 20 over root n. We set that equal to 2. And just to make it easy for you to understand, I'm going to call that 2 divided by 1. That way you can say fraction equals fraction. Any questions on that so far? Then I can cross multiply and say 20 times 1, that's 20, equals 2 times root n. That's called cross multiply. So 20 equals 2 times root n. Divide both sides by 2, and I get 10 times root n. And then I square both sides to get rid of the root, and n is 100. So if I wanted my standard error to be 2, then I need to invest in a diversification of 100 different stocks. Any questions on that? Okay, and again, this does assume that it's diversified and they're independent of each other. which isn't quite true for stocks. Any questions on this idea? Just a note, by the way. Do you think I ever put my money into a single stock? Okay, the answer is yes. Okay, I know it's riskier, but I only put what I call play money into a single stock. I would never put money where if I lost it, I would go hungry because I can't afford food. Does that make sense? But if I have extra money that if I lost, it's not going to ruin my life or even get close to it, ruining my life, then what I do is I use statistics to find the best stock with high variability, but a high chance of high returns. And I look for patterns that other people haven't found statistically. I'll explain that in a couple of weeks, actually, one that I did really well on. And I made hundreds of percent interest, not 9%. Just let you know that you can do that with statistics. Okay, but with risky investment. So never do it with money that it's going to like really hurt you if you lose. Does that make sense? So that's really important. It turns out that you have a higher standard deviation if you have a higher mean for the stock market. So that's just, you know, useful stuff. Okay, so now we can talk about proportions. Now we're going to talk about proportions. Okay, so the first thing is, do you remember we use P for the population proportion? We use P with a hat on top of it for the sample proportion. Okay. And I think I mentioned it maybe a couple weeks ago. We use Greek letters for the mean mu, right? Any guess on, any remember why we don't use Greek letter for P for the population? There's actually a reason. Yeah, it's pi, and it's too confusing for everyone. They think pi is 3.14, etc., and that doesn't work. So I just want to give you a heads up that P in our class, and it's lowercase p, not capital P. Capital P will be the probability. This lowercase p will be the population proportion, and lowercase p will be the population proportion. P with the hat will be the sample proportion. We use Q just because it's the letter after P, okay, to represent 1 minus P. So P is the proportion of people who say yes. Q is the proportion of people who say no. Got it? Because if 70% say yes, 30% say no. So that's why 1 minus P. 1 minus 0.7 is 0.3. Any questions on that little just notation? I do want to give you one more heads up because a lot of people make this mistake. I put P hat here. I will let you know that it's actually really, really tough sometimes to get P hat typed in a computer, okay? Here's what I recommend you do instead. Type in what's in parentheses. P, capital HAT for our class. I'll always accept that. Here's what you don't want to do. Do not, if I ever put P hat in Canvas, which I do because I know how to do it, do not copy and paste that P hat onto your Canvas thing that you're using for your discussion board thing or something like that. And the reason is Canvas has trouble, and often it'll all look beautiful until you hit submit, and then it actually dies and you end up with nothing shown. So that's just a little technical warning. Copying and pasting P hat with Canvas is often a disaster. So do you promise me you won't do that? What is the standard error? Standard error is the standard deviation of the sampling distribution. That's the standard error. Is that what you mean? And the formula is sigma over root n for quantitative data for the mean. Does that make sense? Yeah, so it's sigma sub x bar is the notation. that make sense? Which you can only exactly know if you know sigma. So if you have a sample and you take the standard deviation of that sample, that's not the standard error. Yeah, I did warn you. That's one of the hardest parts about this chapter is there's so many notations. So S is the standard deviation of the sample. Do you remember that? So S is standard deviation of the sample. Sigma is the standard deviation of the population. And sigma sub x bar is the standard deviation of the sampling distribution of means. And that's also called the standard error. So those are the three kind of standard deviations that we have. And they're all different. So you just got to get used to the differences. And then we're also going to have a mu sub p hat, which is the mean of all proportions, of all possible sample proportions. And we'll have a sigma sub p hat, which is a sample, which is a standard deviation of all sample proportions. Sigma sub p hat is also called the standard error, by the way. And here's the big thing is the central limit theorem says the sampling distribution for sample proportions from sample size n has mu sub p hat equals p. That's another way of saying that the sample proportion is an unbiased estimator for the population proportion. Any questions on that idea? Okay, and sigma sub p hat is the square root of p times q over n. And remember, p is a proportion of people who say yes, q is a proportion who say no. If you want, you could write it as the square root of p times 1 minus p over n, whichever is what you like better, is the same thing. Okay, so here is the about the normal distribution, which is, I call it the hardest thing about this whole chapter of all pieces. Do you know my definition of hard? Any ideas of what my definition of hard is? Confusing, not necessarily. Less is easy. No, let me tell you, and I think you'll agree that it's a good definition. The hardest thing means that the proportion of students who get it wrong on the exam or or any of the things they have to do for the class that count for points, that the probability of those who get it wrong is high. And the hardest means it's the highest probability of getting it wrong. Okay, isn't that a good definition of hard for a class? Means lots of people get it wrong. And easy means almost everyone gets it right. So I want to let you know that often more than half of everyone will get it wrong. Okay, so here's what it says. It says if NP is a predicted, so NP, by the way, is a predicted number of yes answers. NQ is a predicted number of no answers. So if NP and NQ are both larger than 5, then the sampling distribution is approximately normal. Okay? So if I do a survey, let's say I did a survey and I asked 50 people. If I asked 50 people, have you been to Africa? I'm going to ask American adults. Have you been to Africa? Do I have a large enough sample size? What do you think? Yeah, the answer is you really have no idea. Do not say that 50 is greater than 30, so it's a large enough sample size. Got it? Okay, it's probably too small a sample size because very few Americans have been to Africa. I've never been. Have you ever, any of you been to Africa? It's very rare to like see someone who's been to Africa. Okay, so if only 5% of anyone who's been in America has been to Africa, then 50 times 5% is 2.5. That's not bigger than 5. Do you see that? So you can't just say it's bigger than 30, therefore it's a big enough sample. Do you see that? So be very, very careful. So here's what I want you to do in the chat box. I want you to type in these words. For a yes, no answer, I will not use the number 30 to see if the sample size is large enough. I want you to type it in. That's your promise. You're going to be promising to me and to yourself when you type it in the chat box. I want you to promise that. Don't just say yes. I want you to type in these words. I'm going to give you a moment or two. It's so, and those who are watching this on YouTube, as a video, write this down because I don't want you to make this mistake. It's the number one mistake. Okay, maybe in the entire class, not just this chapter. This is some reason people can't handle this. So maybe if I make you write it down and promise you won't make this mistake. That's all I can do. Yeah, copying your notes is good too. Okay. Okay, so don't just say I will not use the number 30 to see if a sample size is large enough. It's for a yes, no answer. I will not use the number 30 to see if the sample size is large enough. Got it? If it's quantitative, you're going to use the number 30 to see if it's large enough. But for a yes, no answer, you're not going to use number 30. Do you see how that works? So this is going to be really important for the rest of the entire course. For most of everything we're going to be doing from now on, after reading the question, the first thing you should do is ask yourself, is the survey question a yes, no answer? Has a yes, no answer? Or does the survey question, is it quantitative? Make yourself do that for pretty much everything you do for the rest of this class. And that will help you deal with disasters. Okay? And I already mentioned this for your projects. Remember I said your project survey question cannot have yes, no answers. Do you remember that? Had to be quantitative. And by the way, it'll turn out that that's true for project 2 also. You're going to have to do quantitative. Okay, any questions at all on the central limit for theorem for proportions before I do an example? Yeah, the 2 digits, that was just so you can do the stem and leaf. It turns out for project 2, 1 digit's fine. But I wanted you to practice with stem and leaf. Yeah, let's do an example. Okay. And by the way, this one I actually looked this one up. I was able to find this information online. Okay. You're not going to do proportions for project 2 either, it turns out. Yeah. There's a reason, and you won't understand why until next week. And you're not even ready to think about project 2, by the way. You should be thinking about project 1. Okay. So I actually read on CNN, fewer than half of all Americans approve of the job Joe Biden is doing. Okay. Okay, that was an article I read yesterday. I usually do preparations the day before. Okay, so this is a pretty new. Okay, is this true? I read their study. Not going to get into all the detail, the whole, pages long or whatever. But their sample size was 1,011. Okay. By the way, do you think 1,011 is a big enough sample? What do you think? Okay, we're assuming that they did an unbiased study. Okay, we're gonna assume that. As I mentioned, somebody in this group has someone they care about that works in this stuff. So we're gonna assume that those people are doing things without bias and doing it right. Okay. Okay. So I'm hearing some interesting things. So it's not that at least one person will say yes and at least one person will say no. It's at least, you need to have at least 6 people say yes and at least 6 people say no. Does that make sense? Because you need NP and NQ to be bigger than 5, not bigger than 0. Does that make sense? Because that's the central limit theorem. We want NP and NQ both larger than 5. So we need to say, NP and NQ, that's the number of people that say yes and the number of people say no, needs to be bigger than 5. Any questions on that? So if only one person out of the 1,011 people on average would say yes, then your NP is 1. Does that make sense? Still doesn't make sense? NP is the number of people who say yes. That's what NP is. NQ is the number of people who say no. Okay, P is a proportion who say yes. If you take the proportion who say yes and multiply by the number who says yes, that's the number in the survey, that's the number who say yes. Good, I'm glad it makes sense now. Okay, good questions. Okay. So that would be if we had a sample size of 1,011. Okay, then I went and looked at another survey. No, P is not the number who say yes, it's the proportion who say yes. And the key, P, the first letter of proportion is P. That's why they use P. Okay. So it turns out that I read another survey because they didn't give enough information. And they did a survey of 8,480 Americans. Okay. And of those 8,480 Americans, 39.8% said they approved of the job Joe Biden is doing. Okay, so that was a survey. Okay, it was from a different group of people that did a survey. Okay, there's lots of surveys that could be done. Okay. So now, and this is really important, it's going to be big next week. So I'm giving you a heads up. And also the week after, and the week after that, and the week after that, and the week after that. So if, okay, so remember what we're going to say, is CNN right? Is it really fewer than half? By the way, the highest number that's not fewer than half is what? The highest percent that's not fewer than half is what? What's the high? Sorry, the lowest percent that's not fewer than half is what? The lowest percent that's not fewer than half is what? No, 49.99999 is still fewer than half. 0.5 is the lowest number, not fewer than half. Does that make sense? So we're going to say, well, what if it was 0.5? So we're going to contradict the statement and see if that could even make sense. So if it was 50%, which is like that lowest number that's still not fewer than half. If 50% of all Americans approve of the job Biden is doing, then what's the probability that of a randomly selected, I made a mistake. This was 1,011. I did have a typo there. That of a randomly selected 1,011 Americans, at most 39.8% of them approve of the job Joe Biden is doing. Okay. So just let you know, this is like giving you the reason why we care about the central limit theorem, so that we can calculate these kind of probabilities, which are going to come in a big way in chapters 8 and 9 and 10. Okay. And the idea is that this probability is really, really small, then you would say something is wrong with this statement, because If the probability is really, really, really small and it happens, then you say maybe something we're assuming is wrong. What's the only thing that's assumed in this statement right here? If 50% of all Americans approve of Joe Biden is doing, then what's the probability that a randomly selected 1,011 Americans, at most 39.8% of them, approve of the job Joe Biden is doing? What is the only assumption in this statement as it's written? Actually, the statement doesn't say that. Yeah. This word if right here. If 50% of Americans approve of the job Joe Biden's doing. Okay, so we're testing to see if it could be true that 50%. Okay, does that make sense? And anything higher than 50% would have even a lower probability, by the way, of getting 39.8. So that's what this is really going to be all about for this class. So I'm kind of giving you a kind of a sneak preview of what's coming. So NP is going to be 1,011 times, and we're assuming 50% approve. So if that's P, 0.5, we're making that assumption that that's what P is. By the way, I hope you don't need a calculator. Is 1,011 times 0.5, is that bigger than 5? Yeah, definitely much, much bigger than 5. I'm going to do a double greater than to say, yeah, we're like really no problem. And Q, by the way, that's 1,011 times 1 minus 0.5. Remember, Q is 1 minus P. And that's also, that turns out to be the same. It won't all, we won't always have 0.5 as our assumption, but in this case we do. So that's definitely much bigger than 5. So that means that we have a normal distribution. And if it's much bigger than 5, then it's very normal. It's not even like almost approximately, or you know what I mean? You can like, stake your life on it kind of thing if it's much, much bigger. Okay, so now we're going to go P hat. Okay, P hat is N. Now, what is the population mean of all possible sample proportions? If the population proportion is 50%? What is the population mean of all possible sample proportions? The answer is it's pretty easy, really easy. If the population proportion is 0.5, yeah, P will also 0.5. Not P. P is 0.5, but mu sub P hat is 0.5. That's what that number is, which is always the same as P. So yes, it is P, but I want to emphasize that this stands for mu sub P hat, which equals P by the central limit theorem. Okay, even with a small sample, by the way, the normal is what you need with the large, why you need a large sample. And then what we're going to do is we're going to find our standard error. And that, oh, I think I did it wrong. I want square root first. There we go. And then I want fraction. So that's going to be P, which is 0.5, times Q, which is 0.5 again. 1 minus 0.5 is 0.5. Okay. Sometimes you'll have different numbers, by the way. All over N, which is 1,011. And that, we got to actually calculate 0.5 times 0.5 over 1,011, take a square root. So let's go and do it. The square root of fraction 0.5 times 0.5 over 1011. That's right. There we go, 1011. And there's our standard deviation, about 0.0157 or so. I'll just copy and paste it, because that's easier. Any questions on finding that standard deviation? Okay, so now we can go and do the calculation. We need the low, we need the high. What's the low for this question? Remember, we want to find the probability that of the randomly selected 1,011 Americans, at most 39.8% of them approve of the job Joe Biden is doing. So the low is 0, although typically bunch of 9s. It turns out 0 will work also, but if we're assuming a normal distribution, we should get to negatives also. Okay. And then the high, what's the high? Okay, it's not 39.8 because that's the percent. We need to turn it into a proportion. How do you turn it into a proportion? Yeah, 0.398. Another common mistake people make is they don't remember to turn percents into proportions. Any questions so far? So now let's calculate the probability by going to our calculator. So we have negative 9999. Now we have 0.398. The mean was 0.5. The standard deviation was at 0.015725, etc. P is what we want to find, and I hit calculate. So is the probability about 4.3947? Is that the probability? Yeah, never, ever, ever say the probability is something bigger than 1. What that means is you didn't move your eyeball enough to the right. What do you see on the far right of this probability? Yeah, E negative 11. And I want to let you know, if you use a smartphone, the smartphone, often you're going to have to scroll until you find it, because it's only going to show you some of this stuff. Does that make sense? So that's just a note with smartphones that happens sometimes. So I want to give you a heads up. So that means we have to move the decimal place over 11 places. And again, 4.39, I'll do 4.39. It's good enough. So our probability is 0.10 zeros. And then it was the 439. Any questions on that? Okay, if it's that small, what do you say? No, it's not probable. It's the exact opposite. If it's that small, it's unprobable. It's so unprobable, you would say something went wrong. And went wrong is right here. 50% of all Americans approve of the job Joe Biden is doing. So if you were in charge of, the news agency, then you're going to say that that's wrong, which means now you can put in your headline, fewer than 50% of all Americans approve of the job Joe Biden is doing. Do you see how that works? And we're going to be doing this in a big way for weeks and weeks and weeks. This is day 1 of seeing this. Any questions on this? This is how decisions are made using statistics. Okay, now the last one is essential limit theorem for sums. Now it turns out, if you look at the central limit theorem for means, do you remember the difference between the mean and the sum? If I ask 100 people how much they spent at the market last time they went, and they said, and the mean was $73, then what is the sum of all those, of all the people's answers? If I asked 100 people. Yeah, $7,300. Because you find the mean, you find the sum by multiplying the mean by the sample size. Any questions on that? So that means that you would get mu times n. And similarly, you get sigma times n over root n, which happens to be sigma times root n. And that's going to be the central limit theorem for means. It comes right from there. It's one of those I can actually like talk the math. Okay, you're not responsible for proving it like I just did, but that's what it is. So it says a sampling distribution for sums of samples of size n has mu sub. Do you know how to read that letter right there? That letter. Yeah, that's the sum. It's actually sigma, but not the sigma you're used to. It's capital sigma. Just like in English, our capital letters look different than the smaller letters. In Greek, they do also. And that's the Greek letter capital sigma, and it means a sum. So mu sub sum of x's is equal to n mu. And sigma sub sum of x's, sigma sub capital sigma x, is equal to sigma times root n. Any questions on that so far? And then it turns out it has the same statement about the sample size for getting a normal distribution as we saw with means. And that's if the population's distribution is normal, or if the sample size is large, greater than 30, then the sampling distribution for sums is also normal. Ah, were you on campus when you saw that shirt? That was me. I have that shirt. Oh yeah, I have that shirt. Okay, now you may not remember, but under that it said, and it was delicious. I ate some pie. Yep. And it had the Sigma thing. Yep. So I don't wear it this time of year. I'm not sure where y'all are, but this is what it looks out my window right now. It is snowing, and it'd be way too cold to wear a t-shirt outside. So I'm wearing something warm. Okay, just to let you know. Okay, so the good news is it's really almost the same thing as a sample as a central limit theorem for means, except that we just multiply by n. That's all that is. So here's an example. Suppose that the average customer at a restaurant spends $33.23. Okay. And the standard deviation is $9.22. The funny thing is, I think I wrote this like 10 years ago and I needed to change the numbers. Because 10 years ago, I had a number that was so low you would never spend that at a restaurant. Nowadays, it's like this. Okay. If 65 customers eat at a restaurant today, what's the probability the total revenue at the restaurant will be less than $2,000? Is that clear to everyone what the question is? Okay. And also, what's the first quartile for the total revenue for a day? Okay. That's a typical thing that you care about more than means. If you own a restaurant, you don't care about the mean. You care about the total. Okay. Because the total is the amount of money you have at the end of the day. And that's what you care about as the owner. Does that make sense? That's the most important thing, okay, in economics. So now what we can do is we can say sigma, because that's our variable. It's the sum now. Instead of our x bar, it's sigma. You can write sigma x if you felt like it, but I'm writing sigma. Tilde, that means has the distribution, n, normal. And then we're going to use a big theorem. And that says n times mu. N is 65 because there were 65 customers. Mu was 33.23 because that was the mean. And our standard deviation will be 9.22 because because that was the standard deviation, that's sigma, times the square root of n, which is the square root of 65. Any questions on that? Okay, so now we go ahead and do it. Okay, a mistake a lot of people make is they don't multiply these numbers out. They think it's means, so always pay attention to the keywords like total. So now we're going to do a lot of arithmetic. 65 times 33.23 is $2,159.95. And copy that. Okay, and again, the question was, what's the probability that the total will be less than that, less than 2,000? So, oh yeah, I got to put the mean in first. So less than 2,000 goes negative 9999999. Okay, to 2,000. You could put 0, you'll get the same answer, it turns out. But, technically negative 9999. Okay, maybe people stole money or something. And the standard deviation is 9.22 times root 65. So I took 9.22 times the square root of 65 is 74 times 3, 74.33, etc. I'm going to copy and paste that into our standard deviation. Any questions on that? I want the probability, so that I leave blank and I hit calculate. And I get 0.0157 about. There's my probability. Any questions on that? So notice it's a small chance. It could happen, but it's a small probability. Okay, we also want the first quartile. For the first quartile, what changes? What do I need to change of all my numbers? The low is 9999, negative 99999, the high was 2000, the mean was 2159.95, standard deviation was 74.334, and P was 0.0157. Yeah, I removed the high, but something else I need to change. Yeah, I need to make the P 0.25 because I want the first quartile. And hit calculate. And there's the first quartile. 2,000. I'm going to do it in pennies, although dollars is probably what you'd really care about, but I'm going to go for pennies. $2,109.81. And that'll be the first quartile. Okay, so again, that means around 25% chance, okay, that you're going to end up getting less than $2,109.81 in revenue if you're the owner. Any questions at all on this example? Okay. What haven't I told you yet? Secret word. The secret word is tilde. Tilde. Because remember, we have X bar with a tilde. And I'm going to ask you, by the way, be careful because like on the exam and stuff, I want you to be able to type that in. You can write TILD if you want, or you can type in the letter tilde. I mean, you can write in the shift tilde. That's faster. So the secret word is tilde. Any questions? Okay, I'm going to stop the video. I'm going to stop the recording.